The sound of ocean waves lapping against an underwater dome can be serene, but beneath the Pacific Ocean lies a chilling mystery, a terrifying discovery by the US Geological Survey, USGS, has raised alarms among scientists worldwide. A leak in the ocean floor near Mount St. Helens. This unexpected phenomenon is causing concerns not just for the immediate environment, but for the potential catastrophic effects it could have on our planet. Mount St. Helens and the Cascadia Subduction Zone. Mount St. Helens is a stratovolcano, a steep-sided volcano located in the Pacific Northwest region of the United States in the state of Washington. Its infamous 1980 eruption left an indelible mark on the region and prompted ongoing monitoring of its seismic and volcanic activity. However, it's not just the mountain that demands attention. The surrounding Cascadia Subduction Zone, one of the most tectonically active regions in the world, plays a critical role in the latest findings. This arc-shaped region, stretching from northern California to southwestern British Columbia, is a hotspot for geologic activity due to the subduction of the dense Juan de Fuca plate beneath the North American plate. As these plates interact, water trapped within rocks is released, melting the surrounding material and forming magma that feeds volcanic activity. Sitting about 97 miles south of Seattle and 52 miles northeast of Portland, Oregon, Mount St. Helens is the most active volcano within the Cascade Range and has the highest probability out of all U.S. volcanoes, other than Hawaii and Alaska, to erupt in the future. During the past few thousand years, Mount St. Helens reached its pre-1980 elevation of 2,950 meters, or 9,677 feet, making it the fifth highest peak in Washington at the time, and giving it the nickname of Mount Fuji of America. Recent observations have revealed troubling signs of Mount St. Helens reawakening, but the discovery of a leak on the ocean floor near the Cascadia Subduction Zone has taken the scientific community by surprise. The Cascade Range, where Mount St. Helens resides, is a perfect example of a fundamental concept in geology known as a subduction zone, a place where oceanic crust and continental crust collide. Here, the Juan de Fuca oceanic plate dives beneath the North American continental plate. Oceanic crust is more dense than continental crust, so as the Juan de Fuca plate collides with the North American plate, it is forced downward, deeper within the Earth where temperatures are higher. The ocean crust partially melts at depth and also releases less dense materials, water and gases. The less dense material rises, melting and absorbing surrounding rock as it bubbles upward to form magma chambers. These chambers behave similarly to a soda can, staying dormant most of the time unless a sudden disruption occurs. Can you guess what may disturb the balance in the chamber and set off a volcanic eruption? Earthquakes. Just as a sudden and violent shake of a soda can will cause the liquid to escape quickly when opening, volcanoes will react to this quick change in motion and pressure by erupting onto Earth's surface. The 275,000-year-old geologic history of Mount St. Helens has displayed both relatively quiet outpourings of lava and violent explosive eruptions of volcanic ash and rock fragments known as tephra. Volcanologists have separated the eruption history of this volcano into four main stages, each followed by a dormant, non-explosive period. Ape Canyon Stage. This stage spans from 275,000 to 35,000 years ago and had two major lava dome eruption events. Evidence can be found in rocks as far as eastern Washington, many of which were altered by hydrothermal, hot water activity, indicating explosive eruptions. This stage was followed by a dormant interval from 35,000 to 28,000 years ago. Cougar Stage. The Cougar Stage was one of the most explosive periods for Mount St. Helens, taking place from 28,000 to 18,000 years ago. The explosions varied to form lava flows and domes, large ash ejections, pyroclastic flows, a debris avalanche, and lahars. A debris avalanche is a mass of rock, soil, and snow that runs down the side of a volcano to the valley floor, traveling several kilometers from the source and leaving a horseshoe-shaped crater. Smith Creek eruptive period, 3.9 to 3.3 thousand years ago. Although the shape of the volcano did not significantly change during the Smith Creek period, there were two violently explosive eruptions. One eruption was about 4 times larger than the familiar 1980 eruption, making it the most voluminous eruption over the volcano's history. The other major eruption sourced from an extruded lava dome and sent lahars as far south as the Columbia River. Pine Creek eruptive period, 2.9 to 2.5 K. This period consisted of tephra ejections, pyroclastic flows, dacite domes, and small avalanches which later formed debris fans. Scientists estimate Mount St. Helens' maximum elevation to be about 2,100 meters, 7,000 feet, toward the end of this eruptive period. Castle Creek. Eruptive period, 2.025 to 1.7 Koi. The Castle Creek eruptive period consisted of dacite domes with tephra, pyroclastic flows, lava flows, and lava domes. Recent studies have also shown record of 3 basaltic eruptions, indicating that the chemical composition had changed, a common occurrence in stratovolcanoes. This period built the cluster of domes into composite volcano, ending with a summit elevation of about 2,450 meters or 8,000 feet. Sugar Bowl eruptive period, CE 850 to 900. The Sugar Bowl period was a short dome-building period, with the largest eruption being about 1/10 the size of the 1980 eruption. This eruptive period did not drastically alter the shape of the volcano. Kalama eruptive period, CE 1479 to 1720. The early Kalama eruptive period began with 2 large explosive eruptions, taking place within relatively a short time period between the two. This unique pairing of eruptions is rare among worldwide volcanic studies. A large andesitic eruption took place during the mid-Kalama period, sending pyroclastic flows and hot lahars from the volcano. The late Kalama phase saw the rise of Summit Dome, a dacitic dome that grew over a 100-year period and eventually reaching Mount St. Helens pre-1980 form. Goat Rock's eruptive period, AD 1800 to 1857. This period mainly consisted of smaller eruptions producing ash, tephra, and lava flows. Toward the end of this eruptive phase, the minor eruptions are believed to have been steam-driven without magma rising significantly to the surface. This stage set the final building blocks before the 1980 eruption. The discovery of the leak. The first signs of the ocean floor leak emerged during routine underwater geological mapping in 2015. Scientists from the University of Washington detected unusual thermal imaging patterns and bubbles surfacing near the Cascadia subduction zone, approximately 80 kilometers off the Oregon coast. Upon closer inspection, using remotely operated robotic equipment, they identified a leak seeping from the ocean floor. This phenomenon, dubbed Pythia's Oasis after the Greek oracle, is more than just a peculiar geologic anomaly. It is emitting a unique fluid that is warm, rich in volcanic gases, such as carbon dioxide and methane, and laced with rare isotopes tied to the Earth's crust. Scientists have determined that the fluid originates from the Cascadia megathrust, a fault line where tectonic plates meet. With temperatures reaching 300 to 350 degrees Fahrenheit, the fluid contains high levels of boron and lithium, along with depleted amounts of chloride and magnesium, an unusual combination that suggests the leak is deeply connected to the processes occurring beneath Mount St. Helens. Implications of the leak. The leak's discovery has raised concerns about its potential to trigger catastrophic events. One of the most pressing fears is the risk of a magnitude 9.0 earthquake, known as the Big One, which could devastate the Pacific Northwest. Such an earthquake could generate a massive tsunami, affecting cities like Seattle, Portland, and Vancouver, and potentially rivaling the destruction caused by the 2011 Tohoku earthquake in Japan. Adding to the unease is the possibility of volcanic chain reactions along the Cascadia subduction zone. Volcanologists warn that the connection between the leak and Mount St. Helens could accelerate magma migration, increasing the likelihood of simultaneous eruptions across multiple volcanoes in the region. Historical parallels and future risks. The 1700 Cascadia earthquake, which caused widespread destruction and a deadly tsunami, serves as a sobering reminder of the region's geologic volatility. Today, the stakes are even higher, with denser populations and critical infrastructure at risk. The leak's impact extends beyond seismic activity. Its composition suggests a direct link to the Earth's mantle, raising questions about deeper processes that remain poorly understood. Could this be a precursor to larger, more devastating events? In February 2024, the volcano first observed in 1939 has already erupted several times over the years. The current alert level in the region is yellow, enforcing an exclusion zone of at least 1.5 kilometers as the National Disaster Management Agency, NMA, continues to monitor its activity. Regarding the leak near Mount St. Helens, the United States Geological Survey, USGS, has assured there is no immediate danger. However, scientists are working tirelessly to conduct in-depth research to understand the potential risks posed by this leak. Authorities remain vigilant as geologists race to understand its full extent, while emergency response teams refine evacuation plans. With the Cascadia subduction zone's history of megathrust earthquakes, some experts believe North America is overdue for another, and this leak has only added to growing concerns. Environmental effects from the leak are a pressing issue. Earthquakes and tsunamis are not the only dangers. Chemicals like carbon dioxide and methane, released by the leak, contribute to greenhouse effects. While the current release rate is minimal compared to global emissions, a significant increase could destabilize Earth's balance. Methane, 80 times more potent than carbon dioxide, poses a particular threat. If other methane blocks in the ocean are affected, it could result in an uncontrollable release of methane, further accelerating global warming. Volcanic activities in the region could also release aerosols into the atmosphere. While this may temporarily cool the planet by reflecting sunlight, it could destabilize weather patterns and disrupt agriculture. The surrounding ocean temperatures have already risen, impacting marine life. Many species have fled the region, while some have migrated to the warmer waters, favoring the new conditions. However, the sudden chemical and biological changes could result in mass die-offs for organisms dependent on stable environments. If this leak triggers further disruptions, entire ecosystems could collapse. This natural occurrence may have multiple contributing factors. The Fukushima nuclear incident of 2011, caused by a 9.0 megathrust earthquake and resulting tsunami, introduced radioactive contaminants into the Pacific Ocean. Despite efforts to contain the damage, traces of radiation persisted, potentially impacting the ocean's delicate balance. Additionally, human activities such as oil spills have further strained marine ecosystems. A recent incident involving a grounded Russian oil tanker leaked 200,000 gallons of oil into the Pacific, compounding environmental concerns. Past events like the catastrophic 1980 eruption of Mount St. Helens also disrupted the region's geology and may have contributed to the leak. Efforts are now underway to find solutions. Advanced technologies are being deployed to monitor the leak, collect samples, and analyze its progression. Initial findings suggest the leak is increasing in intensity and size, indicating instability in the magma reservoirs below. As tectonic plate movements are influenced by climate change, scientists expect more leaks to emerge in other geologically active regions. This underscores the need for global collaboration among research institutions and geological survey bodies to better understand these phenomena. Containment technologies to capture gases released by the leak have been proposed, which will reduce environmental impact and aid scientific research. However, logistical challenges, including the storage and transportation of collected gases, pose significant hurdles. Humanity's role in addressing these phenomena is under scrutiny. Are we merely observers of Earth's natural processes, or can we harness advanced technology to mitigate their impact? Perhaps our focus should shift to preparing for life on other planets as these events unfold, or to exploring Earth's unexplored oceans, which remain more mysterious than space. As scientists continue to investigate, the world is left to grapple with the magnitude of what lies beneath the ocean's surface. Each discovery brings more questions than answers, highlighting how little we truly know about our planet. Time will tell if humanity's advances can keep pace with these monumental challenges. The discovery of a leak on the ocean floor near Mount St. Helens has sent shockwaves through the scientific community. As researchers scramble to understand its implications, one thing is clear. The Pacific Northwest remains a region of immense natural power, with the potential to reshape our world in dramatic and terrifying ways. For now, monitoring efforts continue, but the question lingers. What lies beneath the surface, waiting to be unleashed?